Suggest. Oh, these are all practical problems. So there isn't really much in the way of new maths. It's just how do we use what we've learned in the last lesson in maybe physics or chemistry or something like that. Alright, so I can borrow the book there, just slide it around. Before we start, a little bit of vocabulary. What the fudge? Hang on. No. Not working. VGA. That's VGA. No signal. I command you.
Right now program.
I'm running the program. Ah! Well, you see, this is the problem here. The key problem is it's not plugged in. There we go. I apologise, TV. Right, okay. So what makes the previous lesson so useful is how we can use it in physics and chemistry and science. So before we get onto that, just a little bit of vocabulary before we start the practical problems. Right, so we have, I think this vocabulary here, if I said the rate of change of y, what do you think that equals? Yeah. Yeah, not actually this, dy dt.
Oh.
Now, if I didn't want the time, if I wanted to use some other variable, I would say it like this. The rate of change of, y with respect to x. That would be dy dx. An important vocabulary to note, please. Messy. Oh. I get free lunch today. Free lunch. Because there's a new teacher visiting from Cork.
How does she
This reminded me of that conversation we had before about the EAP teacher. Dude, it's good to have ambitions, but don't shoot too high, okay? Yeah.
Don't shoot too high.
Yeah. Stay within your comfort zone, okay? Like, for example, if you're an 8 out of 10, you want to be aiming between 7 and 8, for example, okay? Do you know what I'm saying? What's that? He doesn't understand what I'm saying. Yeah.
I understand, but
if you're the A, you can be the A and B zone, but if you're C, you cannot be A zone.
Yeah, that's right. If you're a C student, you shouldn't be with an A student. Yeah.
Oh, so the
now, I never said what you are. Maybe you're an A student and you're trying for... Yes, well, hang on there now. Okay, continuing. There's more important things than looks, intelligence.
Well, but it's really interesting experiment along the A, B, something like that.
What's he saying? Oh, yeah.
yeah, we can do it. Prove it.
Don't encourage him! Don't encourage him!
Real psychology experiment. If you're A, you don't know you're A, but you need some...
Oh, that psychology stuff's a load of nonsense, please. Not in physics class. It's nonsense. It's nonsense.
Psychology is applicable in science.
Look, I'm going to tell you a secret, okay? Psychology is a load of nonsense.
I've heard a lot of talk like those professionals and they use psychology.
So what? It's a lot of nonsense.
Even
Nonsense.
engineers.
No, nonsense.
When they
Not
create
scientific.
robots.
Fake
But
science.
we can apply that to cognitive science.
Fake science. All fake science.
No.
Fake science. Fake science. Fake science. Just like, remember the mobile phones with the radiation on it? All fake science. Fake science. Fake science. Okay. I feel like Trump there. Fake
It
science.
would be in Sao if it's correct, yeah.
What?
Should like psychology so much.
Fake science. Okay. Continue it. So, proportional. Do we know this word?
Just B, not ED.
Oh, no, that's an AL.
Yeah.
Yeah, sorry.
Okay.
Sorry. Do we know proportional?
Yeah.
What symbol is it? Does anyone know? Yes.
Like a fish.
Like a fish.
Without a fish.
Now, this means A is proportional to B, but if we don't want a proportional, we want an equals.
Okay.
Yeah, we just have to introduce a constant to one of the sides. We can make it like that. Okay, let's have a look at an example. Like I said, these are all sort of physics, chemistry examples, and I want to do a chemistry one for you, because I think you've done this in chemistry already. Reaction rate. Yeah? Have you done reaction rate?
No.
No?
Yeah.
Monica, since you're the only one who remembers.
No.
Monica remembers.
It's a
From his
real
high
relation,
school.
not relation.
But you just said it was your first experiment.
No, it's for laboratory.
Yeah, so?
It's not about the real.
Oh, okay. I don't care. All I want to know is, does anyone know what reaction rate is?
Yeah.
You know what? That's exactly right. Exactly right. So, what letter do you use in chemistry for reaction rates? Do you use a letter?
Fast and slow.
R.
Yeah. Well, normally it would be or.
Oh, what?
Reaction rate.
Reaction rate of, we'll say, some material A, concentration of A. But somebody was about to say there, it's the full definition is for reaction rate is the rate of change of the concentration of A with respect to time. So actually you can write it as a derivative. What would it be? It would be dA over dt. Okay, and somebody might know this, the first order law of reaction rate. Isn't that what it's called? Or what is it? Yeah, the first order reaction. Does anyone know this law? In chemistry? First order reaction law in chemistry. So, just before I continue, what normally happens in the exam is they would give you some kind of law, and you have to change this law into an equation and solve the equation. So, in this example, I'm looking at the first order reaction law in chemistry. Now, I don't know, I thought somebody might know this.
That's the last part of the our semester treatment.
Ah, okay. Okay. Well, anyways, I'll tell you what it is now. The first order reaction law states that the reaction rate is proportional to the concentration. That's the first order reaction law. In other words, it says, if you were to write it as an equation, the reaction rate is proportional to the concentration. Now that kind of makes sense. It means the more of the concentrate, the greater the concentration, the quicker the reaction rate will be. Which, you know, makes sense. You have more of the stuff, then you get more of a reaction. Seems obvious. Okay, so let's change this into an equation. This becomes dA dt, and that will equal Ka. Now look at what I've done here. I've changed this into a first order problem. So if I use my previous method, I could change this into 1 over A dA K dt. Integrating, what do I get here? Log A, and this will be Kt plus C. So that will be A equals E Kt plus C, which equals C E Kt. Now actually we can kind of figure out what the C represents. How could we interpret the meaning of the C? What could the C represent for this problem? Think about how we could get the C. We could figure out what the C is if we knew what the A was when t is 0. Yeah, that's it. When t equals 0, A concentration will equal whatever the concentration at the beginning is, and actually that will end up being C. So we get A equals A0 E K T. Now I could go on to find decay as well, but I would need to give you some other information. So like for example, I'd have to say something like after 1 minute. The reaction experiments you did for your lab. Okay, so what would happen? You'd mix stuff together. How long would you say the whole process lasted for until you got no more reaction?
Huh? Once the temperature stopped rising.
Yeah, but how long did that take?
We don't measure that. That's why I say it's not.
No, just roughly. Like, were you sitting there for hours or?
Wait, let me recall.
Minutes.
10 seconds.
No, this is my
Near 1 minute.
1 minute. Okay.
No.
No, we have shoot it 1 minute.
Okay, so let's put in some examples then. What concentration would you have used as an example?
0.1.
Okay. A0 would be, what would you say? 0.1 molars. Yeah. Good, okay. And we'll also say that A, we'll say is practically all gone. We'll say 0.001 molars. And we'll say after 1 minute, the T is 60 seconds. So after 60 seconds, it's 100 times smaller, so there's not really anything left to happen. So what I want you to do is use that to get the K. So let me just fill in the A0. It's 0.1 EKT. Okay, calculate the K, please.
Teacher.
Yeah.
How you make EKT plus C becomes EKT?
We did that in the last lesson. Didn't we, Lee? We did, but I'll tell you. So what I did was, I changed this into ECEKT. Cool?
Yeah.
C is a constant, agreed?
Oh.
E is a constant, agreed? So together, still a constant.
You should not make it C.
Oh right, sorry. I'll make it A then. B.
Yeah.
No, I got a better idea. C0. There now. Yeah? Got that? What did we get for the K? Probably a negative and small number. Minus 0. So think about what you've achieved. You actually now can graph the time, seconds here, and the concentration in molars, and it starts off at 0.1 and decreases down here to 60.
Never reach 0.
Well, in real life, of course, it would reach 0, but for a simple maths model, it doesn't technically reach 0. Yeah, so you could actually, in the experiment you did in chemistry, if you were counting the time and the temperature, and as long as the temperature is proportional to the reaction rate, so what I mean is, as the temperature changes, that tells us how much reaction is going on, then you could work out the graph for the exact concentration as it decreases in time. Yeah. This is called the first order law. There's a second order law. Do you want to know what the difference is in the second order law?
Inversely.
Nice try. Well, the second order reaction law states that reaction rate is proportional to the concentration squared. No, actually, if it's a squared, it would still have this shape. But I believe, actually, we did squared in. Yeah, actually, look at your examples. Didn't you do one for me earlier today where I said to solve this?
Yeah. Oh yeah.
And you got, I think, 1 over 1 minus x.
Yeah.
Oh yeah.
That graph also decreases, just like this one. Would it decrease as fast or slower? Which is decreasing faster, the E or the X graph here? The E one, yeah. So using this graph would be for some reaction which is not, it's not as rapid as the first order one. Yeah? Got that? Okay, let's do another example. Do you need to write anything down here? Yeah.
Sorry. E to the K, 0.01 K.
You missed a 0.
Where?
In your solve line. How many zeros do you have?
2.1. Yeah.
And how many should you have? Look at the screen. Look here. Oh, 1, 2, 3.
I divide that.
Huh? No. I gave you this. This is given. This is given. I tell you the concentration at the beginning is this,
Yeah.
and then I tell you the concentration 60 seconds later. What are you up to? What? What? I don't trust how your faces are looking right now. No, hang on. What's going on? The three of you.
The thing is,
Yeah. Really? Nothing's going on and you're looking like this?
I might have to you. My hand is different.
Wow.
Oh.
They're weird.
Now I got it. Are you sure? Yeah. Different, right?
What? What's wrong?
You guys are weird.
Human secret. Weird. What? Human secret?
Yeah.
Like similar to that. Right? The symbol. The symbol.
Oh my goodness, I am going to ignore you and continue. I'm glad you didn't say that loud enough for the microphone to pick up. Continue it. Right, let's try number 7, which is quite difficult. Now, this is going to be an English example. Zipf's law states that given some book, the frequency f of any word is inversely proportional to its rank. The rank of the most common word there is 1. The second most common word, I don't think I should have said second. The second most common word of is 2. So anyways, what I'm trying to say here in number 7, imagine you have a big book and you rank all the words from most common to least common. So these are all your words, and here's the rank. Okay, so the most common word would be the. So we call this rank 1. The second most common word, of. This is rank 2. Now what we're really interested in knowing is not the rank, but the frequency. The frequency meaning how often we see this word. So for example, for the first one I tell you the frequency of the is 7%. 0.07. What that means is 7% of words will be the. So if you look at 100 words, 7 of them will be the. And then for the next one, of, what did I tell you? Is 3.5%. I think I have all my info now. Yeah. Okay. So what we would like to know is a formula that can tell us the frequency if we know the rank. So for example, if we are looking at the 10th most common word, how often does that appear? Now you could almost maybe guess what the rule might be. It might be, as we increase the rank by 1, perhaps we halve the frequency. Perhaps. So maybe the third most common word will be about 2%, something like this. But actually, Zipf noticed the law. He said that the frequency is inversely proportional to the rank. So Zipf discovered that the frequency is inversely proportional to the rank. Or yeah, I mistyped that. I should have said the rate of change of frequency with respect to the rank is inversely proportional to the rank.
That's the thing, right?
No, I said the frequency is inversely proportional to the rank. I should have typed the rate of change of the frequency with respect to rank is inversely proportional to the rank. This is Zipf's law, anyways. How do I spell his name? Z-I-P-F, isn't it? Zipf's law. Okay, now I have everything. Let's see what the solution is here. So I have to change this into df dr equals k 1 over r. Cross multiplying, I get 1 over k df equals 1 over r dr. So that means 1 over k f equals log r plus c. I could put the c on whatever side. So I have f over k minus c equals log r. So r equals e f over k minus c, which equals a e 1 over k f, which equals a e b f. I just changed the 1 over k to b. Now, do we have the information to find the a and the b? We do. Actually, I can kind of see what the a is. Oh. No. Am I looking for or am I looking for f? I'm looking for f. So I have to rewrite this, sadly. So I should have now, flip it. I'm looking for f. So now I have, going all the way back here. Okay. F equals k log or plus kc. This is what I meant to do. So f equals, let's just call this a log or plus k times c. We'll just call it b then. So I have my formula for f. I need to find the a and the b now. Okay, so I can look at this and I can look at this. So I get f 0.07 equals a log 1 plus b. That's great, because what does that give me? That gives me b, because this is 0. So I get b equals 0.07. So now I have f equals a log or plus 0.07. Okay, so now looking at the next one, 0.035 equals a log or, which is 2, plus 0.07. Okay, so now I get a equals, okay, that's 0.028 over log 2, which is 0.69. What's that, please, for a? 0.04. Okay, so I have f equals 0.041 log or plus 0.07. So if you know the rank of the word, then you can know how often it appears. Yeah.
So 0.035 minus 0.07 is minus.
Yeah, it's negative.
And then
Whoa!
divided by ln2.
Right.
Run.
Minus 0.035 over 0.69. That's totally what I said.
You did?
Yeah.
Okay. F equals minus 0.05 log 58 log or plus 0.07. Could I clean this up? Could I? I would like to clean it up. It'll make me happy. Can somebody type in E of this number, please? E of 0.07. What's that?
1.07.
Okay, so are you happy if I change this into log 1 point, what did you say?
1.07.
Okay, so log 1.07 actually is the same as that. And you might say, why am I doing that? Well, can you see what I'm trying to... I'm going to try and put them together. I need to do something else though. What should I do to this? Well, I should bring it up to the power. This is actually a 20th. So I can change this into log 1.07 minus log the 20th root of or, which I can change into log 1.07 over the 20th root of or. Now that's as simple and compact as I can make it. Let's just test this out. Can you take this formula, and if we type in 1, we should get 7%, and 2, we should get 3.5%. So Andrew, could you take this and put or is 1, and Monica, could you put in or is 2, and Lee, can you put in or is 3, and we'll see what the next one is.
Well, this is not accurate, because no 1.07 is not even 0.07.
That's what he told me.
It's 0.06. I mean, it's not the exact.
Okay, we'll have to do that. They'll just have to do.
So my one is 1, right?
Yeah. You put in 2?
Yeah.
And what you get?
So
Okay, so because of the 7, it's a bit of an error. So you're 1?
yeah, 0.067.
Okay, and yours is fine. So let's see what you get for 3.
0.0127.
0.0127. So that was probably 1.3 because we're a little bit under. Is that half of 35? Or 3.5%? I don't think so, because that would be 2.6%. So if we double 1.3%, it's 2.6%. What I'm saying is this is less than half of this. Yeah. In other words, where original guess was it's halving each time, but I don't think it's quite halving. I think it's maybe going a little bit slower than halving.
If you use the previous equation, we get 0.015.
Okay, that's fine, but even if we use 0.015, that's still less than half of 3.5. So my point is, it's not quite half. It's so it's actually it's getting smaller faster than what we originally thought. Yeah, so it's actually collapsing pretty quickly, more than what we originally thought. Yeah.
For the equation then, integrate 1 over r.
Yeah.
Yeah, but the next equation is still 1 over r, right?
Huh? No, that's 1 over k.
Oh,
that was just, handwriting. Terrible.
Long k.
Oh no, because k is a constant. So 1 over k is just like a.
Also, when we integrate k, so it's
just a constant. Like if I said integrate a, what would you say it is? Yeah. Yeah. Yeah, this equation is serious as AF. I read the internet too. Okay, continuing. Yes? This is an actual English law about how frequent words are in relation to their rank. So if you were to you could open up a Word document and see how often the word "the" appears compared to the total number of words, and it should be about 7%. So open up a Word document and do a find the word "the," and let's say the Word document has 10,000 words in it. Then this should be about 7% of 10,000. So what's that? About 700. So this law actually seems to be it holds, and I believe it also holds for all languages. Obviously different numbers for different languages and different words, but it seems to hold for all languages. And what's totally strange about this law is not only does it hold for other languages, it also holds for made-up languages, which is really crazy. If you make up a language, this law still holds.
700. I think half of my lab report.
Yeah, but your lab report's not 10,000 words.
Sorry.
Yeah.
You have
the K again.
Yeah, isn't it r over k? Like if it is constant.
Here?
Yeah.
No, in the question I said the relationship is inverse.
I mean the integrate.
Oh, here? No, what I did was I brought the dr up to be with this side and I brought the k down. I swapped the k with the dr.
Yeah, then you integrate the 1 over k, right?
Correct.
Yeah, if you integrate the constant, isn't it 1 to, like, if you integrate 2, and then the answer is 2f.
Correct.
Yeah. So
Yeah. If I integrate 1 over k,
it's r over k.
it's 1 over kf. 1 over k is the constant.
Oh, you find it.
What's confusing you? Dude, if I said a dx, what's this? Ax. True? True or false? True. If I said a df, what's this? AF. Okay? Say it out loud.
Okay.
It's okay?
Yeah,
Okay. What's AF? Why AF? Guys, what's confusing here? What's the problem? Maybe I should have changed 1 over k to a at this point, rather than later. Yeah? Interesting. Let's see. So, number 8's another interesting one. Let's have a look at this one. Yeah, we're finished on number 8. Can I scroll down? No. The rate of change of the time taken for an irregular verb to become regular is inversely proportional to the square root of its frequency. So you know in English you have irregular verbs, of course. Don't do this to me.
Take, took, like that, right?
Take, took, yeah.
Drive, drove.
Can I scroll? Oh, sorry. So a word like
If you put ed at the last, like irregular, if you
take,
put past tense present, took.
Oh.
not,
Take
taked. However, there are some irregular verbs that over time become regular. Example. What is dream? Well, no, it's dreamt. ED now, but that's a recent thing. No, I think there is.
Dreamt.
Dreamt.
You and us have very long.
Check it.
This is so fairy tale. Dreamt.
Dreamt.
Yes, dreamt. What the heck?
I dreamt.
This is so
Fairy
fairy
tale.
tale. This is so fairy tale.
Just MT? No way.
It's true. In dictionary.
Oxford?
What the fudge?
But here that's what is.
Maybe this Irish book.
I never seen you.
The reason I remember this is because it was on a pub quiz once.
Okay. Fake tea.
Shocked, my word.
This is like when I realized Wi-Fi didn't kill me.
Oh, isn't it shock? Different? I mean shock because it's shook, but shock is a shock.
What are you?
Fine.
No?
Oh, this was shock.
Shock. I mean shock. Shock was shook, but we use shock.
Okay, anyway, the point... No, it's fine. The point is...
Oh, yeah.
No, listen. There's irregular verbs, but over time, because if enough people use the regular, then this replaces that.
Yeah.
So, for example, in America, it's dreamed, not dreamt. What was the one you said? There's another one.
No.
No.
Shake,
What
shake,
I say?
shock.
Yeah, shock. SCHOCKED.
I say shock.
Yeah.
Like I shocked by something like that, but isn't it?
Okay. I think the other one is.
Yeah, that's true.
I think the other one is wed, meaning to marry. So, well, that's not that past tense of wed is still wed, but because a lot of people are saying wedded, it's becoming regularized. So, in other words, over time, irregular verbs become irregular. Now, what do you think might be the relationship? What would make an irregular verb become regular quicker? Yeah, the frequency used. So, if the word is used more often, would that make it quicker or slower? No, slower, because if a word is used a lot, then people know what the irregular form is. Like take. This is used so much and it's learned so early when you're so young that for this to become take. Like, I mean, if a kid said this, they would be corrected so quickly. However, words which are not used so often, like wed, it's easy for enough people to misuse it and say wedded. And so it'll take it'll be quicker for this to become regular. This will take hundreds of years to become regular. This is starting to become regular. Maybe in the next 10 or 20 years, then it will just become wedded rather than wed. So, in number 8, what was noticed is the rate of change of the time taken for an irregular verb to become regular is inversely proportional to the square root of the frequency. So the rate of change of the time taken for an irregular verb to become regular is inversely proportional to the square root of its frequency. Now what do I need to put on the denominator?
dt.
Yeah, but a different t.
dt over di.
Like this, is it? Let me just have a peek. I think it's just, I should have said this in the question. I didn't.
Yeah.
Oh my goodness, I didn't know this. I wrote this, but I forgot this.
dt over di.
Help was irregular. In the past it was help.
Oh.
Now it's regular. Help and helped.
No.
Help!
Oh.
Help used to be irregular. It used to be help.
Oh.
Maybe we should start using help in class. I helped Andrew yesterday. I helped.
Weird.
Okay, anyways, what I didn't say in the question, and I'm sorry, I should have said the rate of change of the time taken with respect to the frequency is inversely proportional to the square root of frequency. I didn't say this in the question, it was missing.
Teacher, when we say with respect to frequency, what does that mean? Time taken with respect to frequency?
Yeah, the relationship is, instead of having time in the denominator, I have f. So you want to know, how does the time you have to wait for the verb to become regular, what's the relationship between that and its frequency? So that's why I'm using t and f rather than, because you would like to know if the f is big, we think the t, the time you'll have to wait, will be small.
It was just big.
We were talking about that. Like, it probably, the more frequent a word is. Oh, sorry. No, she's right. It's right. It's the other way.
Well, I'm confused right now. Okay,
the more frequent a word is, the longer it'll take to become regular. Okay.
Oh, okay.
So the relationship we have is this. Let's calculate the answer here. Okay. So dt equals k f to the minus a half df. Are we okay with that? I bring that up there, change it into that, integrate. Right, Andrew, what do I have on the left?
T.
Good. And on the right?
1 over K.
No. K, F, 1 over 2 over 1 over 2 plus C. So T equals 2K square root F plus C. So T equals A root F plus B. So this is what the solution looks like. If this is F and this is T, then the more frequent the word is, the longer it will take. But the increase in the time is the square root of the frequency. So it doesn't grow that quickly. Now I don't give you any numbers, but when I remember it online, I think we got online, they were talking about this. They said something like, for a word like wed, it'll take 5 or 10 more years for it to become regular. A word like take, I think it's like 500 years. Because its frequency is so great, its time will be so great to become regular. I can't remember what help was, but I think it was like maybe 400 years. So if you go back 400 years, it would have been hope. Hope. New word, huh? H-O-L-P. That was the past tense of help.
Yeah.
Not anymore. Now it's helped.
How is H-O-P?
H-O-P. That's hop.
H-O-P-E.
Hope.
I hope so.
Oh, are you saying?
What's the past tense for hope?
Well, right now it's hoped. But I don't know. Was it different? If help was different, then I could believe that hope was different as well. Yeah.
How?
I hate. Okay. Anyways, the point I wanted to make with these two examples was these ODEs work in a very broad range of topics. Once you have some underlying understanding of the relationship. Now you might say, how did they come up with this relationship to begin with? That the rate of change of the time taken with the respective frequency is this relationship here. That's a bit like Kepler's problem. How did Kepler discover the law that he discovered? And again, these things only are discovered from looking at data. So you'd look at a lot of data, and then you would try to figure out some law like this, and then you would solve the law and you would get a formula. This is kind of the idea. So perhaps somebody noticed like words like help. They were looking at this value and discovered the relationship this has with the time taken. But of course it's not. I mean, nowadays you can have computer graphs to help you quickly see what the relationship is. You can imagine this was harder before that. Huh?
And people changes. I mean, even with our mindset. I mean, this formula can't work forever, right?
No, it does work.
No, but people changes, like maybe in the past centuries, people adapt things slower, but then now today people adapt things.
Oh, I understand what you're saying, that perhaps because of the internet it would speed up the process or slow it down. Perhaps so. But I don't...
That word, I found it.
Halt.
China in 1976.
No way, that's crazy
Really?
talk.
The update that always.
Are you saying then in 1975 people were saying halt?
Yeah.
No, I don't believe that.
No, I mean
No,
they.
I don't-
I mean the officially it changed to.
Officially, okay.
1976. But it's
Yeah,
like 100 times. Time is time people use half than the whole video is changing. So you were there, right?
Yes,
So you spoke.
I'm a time traveler.
Oh,
You know
okay.
my secret. I remember when it was halt.
In 1940.
Do you know, if you look at those old YouTube videos from like World War II, look in the background, you might see me on my laptop. And then you'll see someone in the background going, time to go.
The past.
Oh dear. Okay, we're finished there. Right.